Hi, this is Sanjay Gangal from EDACafe. I'm here with Deepak Shankar, founder and vice president of technology at Mirabilis Design. Hello, Deepak.
Hi, Sanjay. It's very nice to be here, and thanks for arranging this meeting.
Well, thank you so much for joining us, Deepak. Tell us about Mirabilis Design.
Mirabilis Design is a software company based in Silicon Valley, specifically Sunnyvale, California. And we provide system-level intellectual property for architecture exploration and analysis using an extremely high-performance simulation platform that allows users to very quickly study the performance, power, and functionality of semiconductors, embedded systems, and software. So using our environment, companies can eliminate all surprises before they start doing the integration or development. We have companies ranging from very large semiconductor companies to startups that are involved in AI SoCs, to large defense contractors building radars and flight avionics, to automotive companies doing autonomous driving and car gateways. The main goal of all of them is to ensure that there is no bottleneck. They size their system correctly, and they partition their software across all the available resources before they go to start doing development. Now, and based on our feedback from customers, we have seen two things that happen. One is they've been able to cut the time it takes for development because they reduce the number of repeats and number of bugs that they would find in the implementation, and they're getting a highly more optimized product. For example, we have a company that went from about 30 minutes of video recording time to 2 hours or 20 minutes of video recording without making any changes to the hardware, just because they were able to look at the entire system, which is the entire camera box, with an adventure camera box, entire camera box, and they were able to look at places where they could reduce the power consumption by combining multiple memory accesses, combining, like different tasks, doing like some shifts between tasks occurring so they're not overlapping. That way get your power down. So a lot of tweaks can be done in your design, even without having to make any difference to your hardware and software. So it's really an environment that allows you to study your entire system before you go to development. Obviously, it can be used downstream, but those are things for you to come to our website and take a look at.
Okay, and how has COVID impacted the design methodology and process for new semiconductors?
We're seeing a huge number of new semiconductor design starts since the beginning of COVID. So when I say beginning of COVID, I'm talking about March 1st, 2020. And the reason I'm seeing that is I'm guessing that we've gotten rid of the water coolers, we've gotten rid of the whiteboards. We now have virtual screens. For some reason, virtual screens seem to be far more productive for people to get more innovation, more creativity out of their heads. The only problem that we've seen in all of these situations is communication. Nowadays, there's no company that's only located in Silicon Valley. I mean, a company on the average will have at least a Bangalore, Ireland, Silicon Valley, and a Shanghai office. So how do you work all of them together? And we have seen a substantial growth in our business, especially in the last year and a half, of almost a 6x jump in revenue and almost a 15x jump in the number of customers, just because of the fact that they want to be able to communicate, maintain a uniform communication across all the customers. So how did we help? We're the only place in the design process for semiconductors where you can get a global view of your entire chip. As you hear my dog confirming that what I'm saying is true. So you can hear us talk away in the background. But you can get the entire view. So as a result of that, people now have a lot of confidence that if they make a change in one part, say they make a change to the gateway security protocol, how does that impact the scheduling on the transmitter side of that chip? They can't do it in RTL. They can't do it in software. But when they have a system level model in VisualSim, they can see, okay, let me make a change here. Boom, here's how it impacts the other side. And immediately they know whether it's a good idea or a bad idea, or they need to make tweaks to it. So I think overall, innovation has increased substantially. And we have aided some of that innovation primarily through better communication and better interaction.
Okay. And several of Mirabilis customers are designing RISC-V products. What are some of the architecture challenges they have encountered?
So there are two things to RISC-V. One is, can we really replace ARM? I think that was the original goal of RISC-V. I'm not 100% convinced by that. But on the other hand, RISC-V has started going, feet to feet with ARM. For example, we're seeing a lot of the controllers on the SoCs or even the AI SoCs that are actually being RISC-V components. So we're seeing that as the first stage. The second stage is we're seeing a lot of R&D, both in universities, but also in research centers, primarily China. That's a major area. We're seeing a huge amount of work where people are looking at, how do I do the same functionality I can get on an x86 or an ARM A77 or an N1 using my RISC-V chips. And what does it mean? It means adding instructions to the ISA, like changing the pipeline, providing different reconfigurable clusters of cores, adding number of cores without increasing the clock speed. They've been trying to do all of that. But what is the challenge really they're facing? A lot of unknowns. With ARM has spent a lot of effort verifying their cores. The RISC-V community is still new. Now, there are some companies that have spent a lot of effort, but RISC-V is still new. So they need to verify every single aspect. And just verifying it at the RTL level or at the DFM level is insufficient because changes in one place may have a huge impact on another one. Example, if I change the number of outstanding requests on my load store execution unit on my processor, it might impact the write backs on my L2 to DDR4 memory. So that is the biggest challenge, is really understanding how it overall hits every aspect of the system. And that's where we get into play. That is what we have seen, that the architecture at that point has a tremendous opportunity, not just like a challenge, it's an opportunity that we have helped enable.
Okay, and can the system-on-chip system models developed by the architecture teams be reused? And if so, where?
Oops, I told everybody they should come to our website to see that. I just already asked that question. The thing is, the system on chip is really a system, meaning that in the past, when you look at a processor, right, when you look at an x86, it was just the x86, it did its own processing. But today, if I look at the AI SoCs, you look at the autonomous chips, you look at the radar chips, you look at the avionics chips, they're much more than just a processing unit. They have accelerators, they have interfaces, they have DMAs, they have so many different functionality in there. Now, the architecture analysis is obviously the first phase where VisualSim models are used, but you also have the challenge. But I've got like 40 or 50 different interfaces, and I got to verify that. And I put that on a Palladium box, or I put that on an FPGA board, that code. How do I know that I'm getting all of this, the sensor data on these interfaces coming at the appropriate time, coming at the appropriate sizes? Only a system overview model can give you that kind of information. And that is another big area where a system model can be reused, which is in the verification after you've got your silicon or pre-silicon stage, but you have your RTL ready. The second area, which is even bigger, is really the software development. Like the software guys need to know what happens if I put this loop here with this control function. Does it actually trigger the jet controller? Or does it actually send this message off to the data center as an IoT and get a response back? So that functionality is also enabled by a system level model. The third one, which is really overlooked by a lot of companies, except for defense contractors, is the area around field testing. A lot of times the chip is actually in a big box that is in a secure area or is in a vehicle that's going around on the street, right? It's impossible to test it in the field. But if you have a system level model, which is what the VisualSim model is, you can replay what is happening in the rear car or in the, say, in a tank or in an aircraft. You can put that in the model and then recreate the same scenario and figure out where the problem is. So the system model can go beyond to doing, like chip level or RTL level verification on a board or on an FPGA. Can be used for the early software validation and can also be used for field testing.
Okay, and you have recently introduced hybrid processing, a new concept to architecture exploration and system level analysis. Why is it called hybrid processing?
Very good question. It's it's something that we've been thinking for a long time, and I think the industry has also been trying to do it, but they haven't really had a success. So this is kind of our first foray into that. See, the challenge is there are so many different parts of the design process where system models are required. You have the conceptual, like an R&D engineer. You have the development architect. You have the marketing guys. You have the customer that's going to try to integrate this chip into a bigger system. Now, the commonality of all of them is they need models to be able to verify all of these, right? Now, what is common among all of them? Your interfaces are common. The sensors or the input internet or input Ethernet or any of those are common. Your output, which is either an egress port going out to the internet, or it's a display, or it's feeding it into an instrumentation panel. Any of those things are common. What we have done with the hybrid processor is we allow you to reuse the same model across the design process. Now you might say, hey, that's not a big deal. If I have those external things in C++, I could do it very easily. Yes and no. The problem is every model, right, that is being used at those different levels for the inside of the chip, it tends to be completely different. Interfaces are completely different. The structures, or what we call the transactions, are completely different. What we've done with the hybrid model is we've created a stochastic model that a concept engineer can use. We've created the transaction level model that a development engineer can use, a verification guy with a cycle accurate model, and also the same thing can be used by customers. Now, the interesting thing is all of them have the same interface. So I just swap out one, put the other one, I have it. That is one side of it. The second side of it is the fact that these models have different levels of data available. For example, I might have all the details of the cache and the memory, but very little on the pipeline core. Or I might have the pipeline core, the cache and memory, but very little details of software. Or I might have all of them. Or I might have none of them, so which means just a delay. We have building blocks in this hybrid processor IP that emulates all of this functionality. Or you don't have software? No problem. We have a profile-based software generator. Or you don't have the cache addresses? No problem. We have a tool that can very intelligently generate those addresses based on your profile of your software. So we've created a whole umbrella of items that allow anyone that's building a new SoC to be able to pick this up and select from that library of IPs what exactly he would require. And that's why it's hybrid. There's this whole concept of triple net. It's kind of the same thing, right? Hardware, software, networking, stochastic, transaction level, cycle accurate, model construction, simulation, analysis. So that's your triple net that you get out of this thing.
I see. And so Mirabilis Design is the first to advocate power analysis as an integral part of system design. What benefit does power performance trade-off bring to a design team?
When I look at anything, what do we have? We have phones, we have electric vehicles, we have cameras, and we have IoT devices, we have aircraft, we have satellites. If you look at any of the news that comes in your EDACafe, it's always around these topics of application. Every one of them has a common theme: power. Tesla says I can drive 600 kilometers, right? My iPhone says now you can run it for 2 days without charging. So when you think about all of that, it goes to power. What we're advocating is when you're starting to think about building a new product, do not just think of performance, area, weight and size. Think about how does it impact the power. I'll give you a real life example. We had a customer that was designing a chip, And they initially had like about a 1.5 gigahertz core to be, to be able to meet the requirements for all their 4 different threads that were running on top of it. Now, what we ended up doing was we helped them where we incorporated power into all the building blocks. That way, all of our hybrid processor blocks already have power incorporated into it. So the user just needs to update a table and they're all done. But here, what we ended up doing was when we incorporated the power, they could actually see every time there was these processing happening, huge spikes, which means my thermal cost is going to go up, my chip cost is going to go up. So what we helped them do is we created some offset numbers. So their tasks all don't align up at exactly the same time, or their memories don't align exactly the same time. So when we did that, boom, the power just dropped. And because we did the offset, they started saying, hey, wait a minute, I can try this at 1 gigahertz. I can try this at 8. So we went from about 1.5 gigahertz to about 776 or 780 or some unique number. It wasn't an exact multiple. They went with that one. So guess what? Price went down. My thermal cost went down. The amount of power went down. Their battery life went down. And I had the same performance. So that power performance trade-off must be made an integral part of your development process. It should not be an afterthought. It should be the main focus of your design.
Now, Mirabilis Design has over 500 library components, and all of them have been built in-house. Why not just depend on vendor models? And how do you ensure accuracy to the real hardware?
Good question. Actually, the accuracy to the real hardware is the bigger question than the first one, because people are like, how do I trust you? Right? It's a really tough question. But the reality is that what we do is we have a very stringent verification process. So we have about 40 benchmark markers, and everything that we go through goes through those 40 benchmarks. So only when we pass through those 40 benchmarks, we say, yep, this is correct. Now, there are 2 types of models that we get. One of them is models for which IP is already available. Maybe it's in an FPGA, maybe it's a commercially available chip. So we can get data out of it. But majority of the time, nothing is available. So let me answer the first one, which is where something is available. So what we would do, we would load the software, we would run it, we would generate all the statistics from the real chip, put it into the model, and we test. What are these benchmarks? Some of these benchmarks could be that I'm accessing the cache. Some of them are interfaces sending data to DMA. Others might be that it's doing only an integer activity in the pipeline. So they're all either combination or dedicated functions. So now, because I have data from a real chip, I'm able to verify it. But at the same time, I have this scenario where there's no data available. Matter of fact, even the spec is not complete. In those cases, what we do is we actually use the old-fashioned way of putting columns and cells in Excel and verify it that way. So we start with a simple scenario, slowly build up on it, and we verify that, yes, this is working correctly. So that is on the accuracy part of it. And that's why, we have a lot of success stories that we've, highlighted the accuracy. We did a webinar, I think a few weeks ago, where we even compared the power between a chip that has an A77 ARM Cortex and another chip with ARM Cortex A53, and a third one with Sci-Fi's RISC U74. And we were able to show the performance and power difference between those 3 different chips, all having 4 cores in them. So it's really a way that we could say, yep, we can confidently verify that. Why don't we use vendor models? 2 problems. First problem is very few vendors actually provide architecture models. Matter of fact, even like the largest supplier of IP processor cores has stopped providing vendor models for certain processors. Then there is the other one, which is these models, each one of them would have its own interface. So now if you're going to try to integrate all of them, it becomes a nightmare. So then we're expected to fix everybody's thing to provide custom wrappers. When you have 200 vendors, it's very hard to do that. Mm-hmm. So those are the 2 reasons why we decided to go with building our own models.
And what is the best way for our audience to find out more about Mirabilis Design on the internet?
Oh, the best way to do it is to go on our website, which is www.mirabilisdesign.com, Mirabilis Design, not Mirabilis, mirabilisdesign.com, as if you'll find a flower in California. That's mirabilisdesign.com. And you go to this thing called Launch IP, Launch Demos. So when you do this launch demos, you can actually see a list of over 200 different demos. You can click on one of them and it goes through a small process, and you can bring up a model and run a simulation right on your desktop. No other software is required on your desktop. Nothing is required. You can run a VisualSim model right off the website. So you can immediately go see, okay, I want to see what an A53 does. I want to see what an A77 does. Boom, you have that capability right there. That's the best way to learn. Yeah.
Very cool.
Thank you.
So, Deepak, is it okay if I ask you a couple of personal questions?
Oh my God, is this like one of those Ellen DeGeneres shows?
I just want to have some fun. I mean, you've been giving all the technical answers. I thought let us have a little fun at the end. So, Deepak, what do you do for fun outside work, or what is your personal passion outside work?
Sports. So I'm a rower. I'm into tennis. I'm into bicycling. I'm into running. So rowing, for example, I took it up about 8 years ago when I moved to India from Silicon Valley. And when I did that, I started training. And 2 years ago, I participated in the National Senior Masters in India for what's called the double scull. And I ended up getting a bronze medal.
Wow, congratulations.
Yeah, thank you. So yeah, so sports are really my passion. So anytime I get a break, like for example, today, right after the meeting, I get tired. I just take my cycle and I keep driving. And after a while, I get really tired and I say, okay, I'm going to come back home. Kind of like Forrest Gump. That's kind of what I do. I just like exert myself. I'm like tired. I'm going to come back. So that's what sports is my whole life.
Okay. And are there good rowing places near your home?
Yes, they are. We have the Madras Boat Club, which is about 156 years old. And it's I think, the second oldest boat club in Asia. And it's among the top 10 oldest boat clubs on the planet. Wow. And we have about a total of, like round trip, we can get a total of about 12 kilometers of rowing. It's about 6 kilometers full length. Yeah. So we get a pretty good exercise.
Oh, pretty nice. Pretty nice. And Deepak, can you also share something about yourself that most people at Mirabilis Design who work with you don't know about you? And don't get in trouble.
Yeah, I know. So I should make sure the people at Mirabilis don't listen to this podcast. That's probably the most important thing. No, when I think about it, I think the biggest thing that people don't know is the kind of the other fun things that I do. I'm involved in a lot of teaching of like basic math, like basic physics. I started off teaching my daughter, just like Khan Academy. He started teaching his nieces. I started teaching math, but then what I would do is for my daughter's classmates, I would create question papers, practice question papers for them. So before every exam, I'd create a practice question paper so they would go, so they could go work on it so that they would be really prepared for the examination. So I started doing this as a hobby, and it's starting to become a regular feature for me. And it's kind of fun because you suddenly realize, man, I should have really studied harder in 7th, 8th, and 9th grade. I goofed off way too much.
That's pretty nice. Well, thank you so much, Deepak, for taking time to record this interview. Have a great day and stay safe.
Thanks a lot, Sanjay. And it was like a great opportunity. I really appreciate it.
Okay, this is Sanjay Gangal from EDACafe.